You built the most powerful machine humanity has ever created to answer one of the oldest questions in existence. What is reality made of? Deep beneath the border of Switzerland and France, protons race at nearly the speed of light, carrying energy so extreme they recreate conditions from the first moments after the Big Bang. But something unexpected began appearing in the data. Tiny anomalies, statistical whispers, signals that should not exist. Most disappear. A few refuse to go away. And those few may be telling us something extraordinary. So, before you settle into the story, take a moment to like the video and subscribe if you enjoy exploring the deepest mysteries of science. And tell us your location and local time in the comments below. Now, let's begin. Imagine standing in an ordinary field near Geneva. The grass moves gently in the wind. Cars pass on distant roads. Nothing about the landscape suggests that beneath your feet lies one of the most ambitious machines humanity has ever built. But 100 meters below the surface, hidden inside a circular tunnel stretching 27 kilometers, something extraordinary is happening. Protons are being accelerated to speeds so close to the speed of light that the difference becomes almost meaningless. They circle the tunnel more than 11,000 times every second, guided by superconducting magnets colder than outer space itself. Then, at carefully chosen points, they collide. Not like cars crashing on the highway, more violent, more fundamental. These collisions release bursts of energy so intense that for fractions of a second, they recreate conditions that existed just after the Big Bang. You are not simply smashing particles together. You are reopening the earliest chapter of cosmic history. And the reason humanity built this machine begins with a deeply unsettling realization. Despite centuries of scientific progress, we still do not fully understand what reality is made of. That ignorance is more surprising than it sounds. By the early 20th century, physics looked almost complete. Isaac Newton had described motion. Albert Einstein had rewritten space and time. Atoms had gone from philosophical speculation to measurable fact. Many believed the major mysteries were behind us. The remaining work some thought was merely filling in decimal places. Then, reality broke apart. Literally. Scientists discovered that atoms once believed indivisible were themselves made of smaller components. First came electrons, then nuclei, then protons and neutrons. And then, something even stranger happened. Protons and neutrons also turned out not to be fundamental. They contained smaller particles still. Reality, which once looked like solid stone, began to resemble nested Russian dolls, each layer revealing another hidden inside. Every time physicists thought they had reached the bottom, nature presented another door. That pattern changed how scientists saw the universe. Matter was no longer a collection of tiny billiard balls. It became something stranger, more elusive. Quantum mechanics revealed that particles behaved like both objects and waves. Sometimes they appeared localized like grains of sand. Other times they spread like ripples across water. Worse, the act of observation itself changed outcomes. The deeper scientists looked, the less intuitive reality became. Imagine trying to understand an ocean by examining a single drop, only to discover the drop changes shape every time you touch it. That was modern physics. The closer you looked, the more bizarre nature became. By the mid-20th century, particle physicists found themselves overwhelmed by discovery. Cosmic ray experiments and early accelerators uncovered not just a few new particles, but dozens. Mesons, baryons, resonances. Exotic states with lifetimes so brief they vanished almost instantly. The growing list became known as the particle zoo. It was chaos. Nature seemed to be producing particles the way a storm produces raindrops. Patterns existed, but they were buried under overwhelming complexity. Scientists needed order. They needed a map. That map began emerging in the 1960s. Physicists proposed that many known particles were not fundamental at all. Instead, they were combinations of smaller building blocks called quarks. At first, the idea sounded almost absurd. Quarks had fractional electric charges, something never observed in isolation. But the mathematics worked. Over time, evidence accumulated. More experiments confirmed the model. Slowly, chaos became structure. What once looked like hundreds of unrelated particles could be understood as combinations of a much smaller set of ingredients. This was revolutionary. Imagine walking into a giant library filled with millions of books written in countless languages, only to discover every word in every book was formed from the same alphabet. That was the power of the emerging particle framework. Diversity emerged from simplicity. Beneath complexity lay order. And yet, one question refused to disappear. If matter is built from fundamental particles, what gives those particles their properties? Why does one particle have mass while another does not? Why does light travel forever while heavier particles resist acceleration? Why is matter stable at all? These were not small questions. They touched the architecture of existence. To answer them, physicists needed more than theory. They needed experiments at unprecedented energies. Because the universe hides its deepest layers behind energy barriers. The smaller the scale you wish to observe, the more energy you need. This is one of the strangest truths in physics. Seeing smaller requires hitting harder. There is an analogy that helps. Imagine trying to understand the structure of a watch sealed inside a steel box. Looking at the box tells you almost nothing. But if you strike it with enough force to shatter the casing, internal components scatter outward. Springs, gears, screws. Suddenly, the hidden structure becomes visible. Particle accelerators work on the same principle. By smashing particles together at enormous energies, scientists break apart the invisible machinery of matter and analyze the fragments. That philosophy drove the birth of increasingly powerful accelerators. Each generation reached deeper into reality. Each machine expanded the frontier. Smaller mysteries became visible. New particles emerged. The standard model of particle physics gradually formed, becoming one of the most successful scientific theories ever developed. It described the fundamental particles and the forces governing them with extraordinary precision. But precision created its own problem. The better the theory became, the more glaring its absences appeared. It could describe electromagnetism. It could explain nuclear interactions. It predicted particles before they were discovered. Yet, it could not explain gravity within the same framework. It could not explain dark matter. It could not explain why the universe contains more matter than antimatter. It could not explain why particles had the masses they did. There were cracks in the foundation, and so the dream of a new machine was born, not just another accelerator. The ultimate collider, a machine so powerful it could probe energies never before reached on Earth. A machine capable of recreating the primordial fireball that filled the universe less than a trillionth of a second after the Big Bang. A machine designed to hunt the final missing piece of the standard model and perhaps reveal something beyond it. That machine became the Large Hadron Collider at CERN. Constructing it required decades of engineering, international cooperation, and staggering precision. Thousands of scientists and engineers contributed. Magnets weighing tens of tons had to align with accuracy thinner than a human hair. Superconducting systems required temperatures near 1.9 Kelvin, colder than the cosmic microwave background left over from the Big Bang. Data systems had to process collision events occurring hundreds of millions of times per second. And all of this served one purpose: to ask nature a question. What lies deeper? When the collider finally came online, excitement mixed with tension. Physicists expected discoveries. Some hoped for supersymmetry. Others expected dark matter candidates. Many believed new physics would emerge quickly once the energy frontier opened. And for a time, that optimism seemed justified. The machine worked. The detectors saw collisions of breathtaking complexity. Hidden among trillions of interactions were rare events carrying the fingerprints of fundamental truth. Each collision became a message from reality itself, encoded in showers of particles and traces of energy. Most collisions told familiar stories, but a few did not. At first, these anomalies were easy to dismiss. Noise, statistical fluctuations, detector artifacts. In particle physics, false alarms are common. Strange patterns appear, attract attention, and disappear once more data arrives. That is normal, but sometimes a signal lingers. Sometimes a whisper survives. And when it does, physicists become very uncomfortable, because history has taught them something profound. Nature rarely whispers without reason. And deep beneath the earth, inside humanity's most powerful machine, something had begun to whisper. The question was no longer what CERN was built to find. The question had become far more unsettling. What if CERN found something nobody expected? By the time the Large Hadron Collider began operating at full power, physicists had already spent decades assembling what many considered the greatest intellectual achievement in modern science, a framework so precise that it could predict the behavior of subatomic particles to astonishing accuracy. This framework became known as the Standard Model. On paper, it looked elegant, almost beautiful, but beauty in physics can be deceptive. Sometimes the most polished structure hides the deepest cracks. To understand why CERN mattered so much, you first need to understand what physicists believed they had already discovered. Strip away every object around you. Remove buildings, oceans, mountains, planets, stars, even galaxies. Keep zooming inward until everything familiar dissolves into particles. According to the Standard Model, nearly everything you see is built from a surprisingly small set of fundamental ingredients. Not hundreds, not thousands, just a handful. Matter begins with two families of particles, quarks and leptons. Quarks combine to form protons and neutrons, the dense cores of atoms. Leptons include particles like electrons which orbit atomic nuclei, and neutrinos which pass through your body by the trillions every second without leaving a trace. These particles are not merely tiny objects floating in space. In modern physics, they are excitations of deeper quantum fields that permeate the universe. That means what you call a particle is closer to a ripple than a marble. Reality at its deepest level behaves less like solid matter and more like vibrations on invisible cosmic fabrics. This idea is difficult to picture because everyday experience trains you to think in objects: chairs, stones, bodies, planets, stable things with clear boundaries. Quantum physics destroys that intuition. Imagine an endless ocean extending in every direction. You never see the entire ocean. You only see waves rising and falling at its surface. In this analogy, the ocean is the quantum field. The waves are particles. Electrons are waves in the electron field. Quarks are waves in quark fields. Even light itself emerges as vibrations in the electromagnetic field. Suddenly, matter stops feeling solid. It becomes motion, pattern, excitation. This was the first profound revelation. The second was even stranger. Particles do not interact randomly. Their behavior is governed by forces, and in particle physics, those forces are carried by other particles called bosons. Photons carry electromagnetism. Gluons bind quarks together through the strong nuclear force. W and Z bosons mediate the weak force responsible for radioactive decay and stellar fusion. These force-carrying particles act like messengers constantly exchanged between matter particles, transmitting influence across space. At first, this sounds abstract, but there is a useful analogy. Imagine two ice skaters throwing heavy medicine balls back and forth while standing on frictionless ice. Each time one skater throws or catches the ball, they recoil slightly. That exchange creates motion between them. In a similar way, forces emerge through particle exchange. Matter communicates by trading invisible messengers. And remarkably, the mathematics worked. Again and again, experiments confirmed predictions with absurd precision. The magnetic behavior of electrons matched theory to more than 10 decimal places. Particle collision outcomes aligned with calculations. Rare decay processes occurred exactly where expected. The Standard Model became physics' masterpiece. And yet something felt wrong, because a perfect map is not the same as a complete map. The first crack appeared when physicists asked a deceptively simple question. Why do particles have the masses they do? This sounds innocent until you realize mass shapes almost everything. Mass determines how matter clumps into stars. It governs chemistry, structure, biology, and the very possibility of complex life. If electrons were much heavier, atoms would behave differently. If quarks had slightly different masses, stable, nuclei might never form. Reality depends sensitively on these numbers, but the Standard Model in its earliest form had a problem. Its equations naturally wanted many particles to be massless. That contradicted reality. Something was missing. Physicists proposed an extraordinary solution. They suggested that all of space might be filled with an invisible field, not localized, not concentrated in one region, everywhere. Particles moving through this field would interact with it to different degrees. Some would glide through almost unaffected. Others would resist behaving as though they possessed mass. Imagine walking through a crowded swimming pool. A fast swimmer passes easily. A person dragging heavy gear struggles. Both move through the same water, but resistance differs. That resistance creates an effective heaviness. This was the central intuition behind the Higgs field. If the field existed, it solved the mass problem, but it introduced another mystery. If this field permeates all space, there should be a detectable quantum ripple associated with it. A particle. One particle, the Higgs boson. For decades it remained hypothetical, and this is where the stakes changed. Because without the Higgs, the Standard Model broke apart. Without it, the equations became unstable at high energies. Particle interactions would violate fundamental constraints. The elegant structure that explained so much would collapse. The missing particle was not optional. It was essential. So, when CERN built the Large Hadron Collider, one target towered above all others: find the Higgs. But even as physicists pursued that goal, a more unsettling truth lingered beneath the excitement. The Standard Model. Despite its success, was incomplete in ways impossible to ignore. Consider gravity. Every object you have ever touched is shaped by gravity. It governs planetary orbits, black holes, galaxies, and cosmic structure. Yet gravity does not fit cleanly into the Standard Model at all. The theory that explains particles with astonishing precision says almost nothing about one of nature's most familiar forces. That alone was alarming, but the problems went deeper. Astronomers had discovered that visible matter makes up only a tiny fraction of the universe. Galaxies rotate too fast. Clusters bend light too strongly. Something invisible exerts gravitational influence on enormous scales. Scientists call this dark matter. Whatever it is, it outweighs ordinary matter several times over, and the Standard Model has no confirmed particle that explains it. Then came another mystery. The universe contains matter. That sounds obvious until you remember antimatter exists. Whenever energy creates matter, it should create equal amounts of antimatter. Matter and antimatter annihilate on contact. If the early universe produced equal quantities of both, everything should have annihilated into radiation long ago. And yet you exist. Stars exist. Galaxies exist. Why did matter win? Again, the Standard Model offered only partial answers. By now, the picture becomes unsettling. Imagine inheriting a magnificent mansion. The architecture is flawless. The engineering is extraordinary. Every visible room is carefully designed. But as you live there, you notice locked doors, hidden staircases, entire wings missing from the blueprint. That is modern particle physics. The mansion stands, it functions, but parts of reality remain inaccessible. CERN was built to open those locked doors. Physicists hoped that once the collider reached sufficient energy, nature would reveal new particles. Supersymmetric partners, hidden bosons, dark matter candidates, entire sectors beyond known physics. Many expected discoveries to come quickly. After all theories predicted them, mathematics suggested them, naturalness seemed to demand them, but nature does not care about human expectation. And this is what made the next development so unsettling. The Large Hadron Collider did exactly what it was designed to do. It smashed protons at unprecedented energies. It produced enormous datasets. It hunted the Higgs, and then it found it. That should have been the moment physics celebrated victory. In some ways it was, but almost immediately, a strange discomfort began spreading through the scientific community. Because the Higgs solved one problem, while making a much bigger problem impossible to ignore. Why did the universe choose this Higgs? Why this mass? Why this exact value? The answers disturbingly did not make sense. And for the first time, some physicists began to wonder whether the Standard Model's greatest triumph might also be hiding its deepest flaw. That flaw would soon acquire a name, the hierarchy problem, and it would become one of the reasons anomalies at CERN started to feel far more dangerous than anyone expected. Long before the Higgs boson became a headline, before news anchors called it the God particle, before billions of dollars and decades of engineering converged beneath the Earth. The particle existed only as a mathematical necessity, not an observation, not a detection, a gap in equations. And sometimes in physics, that is where the most important discoveries begin, not with something you see, but with something reality refuses to explain. In the early 1960s, particle physics faced a growing crisis. The equations describing the electromagnetic force worked beautifully. Quantum electrodynamics had become one of the most accurate theories ever developed. But when physicists attempted to unify electromagnetism with the weak nuclear force, the mathematics began to collapse. The theory demanded symmetry, an elegant balance in the equations that treated force carriers in a unified way. But there was a devastating contradiction. Symmetry naturally implied that certain force-carrying particles should have no mass. Reality disagreed. The photon, the particle of light, is massless. That makes sense. Light travels at the cosmic speed limit because nothing slows it down. But the weak force is carried by two heavy particles, the W boson and the Z boson. These particles are enormous by subatomic standards, roughly 80 to 90 times heavier than protons. Their mass explains why the weak force operates only across tiny distances inside atoms. But their existence created a paradox. How could a unified theory predict massless force carriers while nature clearly contained massive ones? That contradiction threatened to destroy the entire framework. Then came a radical idea. Several physicists working independently, including Peter Higgs, François Englert, and Robert Brout, proposed a mechanism so strange that even many experts initially struggled to accept it. What if empty space was not truly empty? What if the vacuum itself possessed structure? This sounds almost philosophical, but in quantum physics, vacuum does not mean nothing. Vacuum means the lowest energy state of all quantum fields. Even in apparent emptiness, fields still exist. They fluctuate, they vibrate, they influence particle behavior. The new proposal went further. It suggested that one particular field filled every point in the universe. Every atom, every star, every galaxy, every region of interstellar void existed inside it. Unlike other fields, this one had a non-zero value even in empty space. It was always there. This became known as the Higgs field. To understand why this mattered, imagine a large room filled with people standing shoulder to shoulder. A celebrity walks in. Instantly, people gather around, slowing movement. Progress through the room becomes difficult. Now imagine an ordinary person entering instead. Fewer people cluster around them, so they move more freely. Both individuals move through the same environment, but one experiences more resistance. That resistance is the analogy for mass. Particles moving through the Higgs field interact with it to different degrees. Strong interaction produces greater resistance, which appears as greater mass. Weak interaction produces less resistance, meaning lower mass. No interaction means massless motion, like the photon. This solved the paradox beautifully. The equations preserved symmetry at a deeper level while explaining why some particles behaved as if they were massive. It was one of theoretical physics' most elegant breakthroughs, but elegance alone proves nothing. The idea came with a critical prediction. If the Higgs field existed, it should occasionally produce measurable quantum excitations. A ripple in the field, a particle, the Higgs boson, and there was the problem. No one had ever seen it. For decades, the Higgs remained a ghost in the mathematics. Theoretical physicists refined predictions. Experimentalists searched increasingly higher energies. Collider after collider pushed deeper. Yet the particle stayed hidden. It became both famous and frustrating. Entire careers were spent chasing it. Why was it so difficult to find? Because the Higgs is extraordinarily unstable. If created in a high-energy collision, it survives for roughly 1/70th of a second before decaying into other particles. No detector observes the Higgs directly. Instead, scientists search for decay signatures, the particle's fingerprints left behind in showers of secondary particles. This is like trying to prove lightning struck a forest, not by seeing the bolt itself, but by reconstructing the burn patterns on the ground after the storm. You infer the invisible event from its consequences. That required enormous data. It required energies no previous accelerator could reliably reach. It required CERN. When the Large Hadron Collider began generating collision data, the search intensified. Two gigantic experiments became central to the hunt: ATLAS collaboration and CMS collaboration. Each detector was a technological cathedral built to capture collision debris with extraordinary precision. Layer upon layer of sensors recorded particle tracks, energies, momenta, and decay patterns. Every collision became a puzzle. Most puzzles led nowhere, but hidden among trillions of proton collisions were rare events that mattered. Physicists analyzed mountains of data looking for tiny excesses above expected background noise. They searched across multiple decay channels. Higgs decaying into photons, into Z bosons, into W bosons, into bottom quarks. Slowly, a pattern emerged. At around 125 gigaelectron volts, both experiments saw something unusual. Not a dramatic spike, not an obvious signal, a subtle excess. But it appeared repeatedly, in multiple datasets, in independent detectors. The statistical significance grew. Then came July 4th, 2012. Inside CERN, anticipation was electric. The auditorium filled with physicists who had waited decades for this moment. Many already suspected what the announcement would reveal, but science demands evidence, not hope. The results were presented carefully. Confidence levels, significance thresholds, background rejection. Then the conclusion arrived. A new boson had been observed. Its properties were consistent with the Higgs. History had changed. Applause erupted. Some scientists cried. Peter Higgs himself sat visibly emotional. For nearly half a century, a particle born in theory had finally emerged in data. It was a triumph not just for CERN, but for science itself. Humanity had predicted something invisible, built a machine to test reality, and found exactly what theory demanded. This should have been the moment of completion. It was not, because almost immediately something strange became clear. The Higgs existed, but it had the wrong mass. Not wrong in the sense of measurement error, wrong in the sense that theorists hated its value. The Higgs mass was approximately 125 GeV, heavy enough to matter light enough to create a profound theoretical headache. According to quantum mechanics, the Higgs should receive enormous corrections from interactions with virtual particles constantly flickering in the vacuum. Those corrections should push its mass toward vastly higher values, potentially near the Planck scale, where gravity becomes quantum. Instead, the measured value was absurdly small compared to those expectations. To make theory fit, observation required astonishing fine-tuning. Imagine balancing a pencil perfectly upright on its tip during a hurricane. That is what the Higgs mass seemed to require. Tiny quantum contributions from enormous energy scales had to cancel each other with unbelievable precision. Many physicists found this intolerable. Nature rarely appears that delicately tuned without deeper explanation. This became one of modern physics' most unsettling puzzles, the hierarchy problem. Why is the Higgs mass so small compared to the largest scales in physics? Most theorists believed the answer had to involve new particles or new symmetries. Supersymmetry was a leading candidate. Hidden partners for known particles could cancel dangerous quantum corrections naturally. And that was the expectation after 2012. Now that the Higgs had been found, the next discovery should come quickly. New physics should appear: supersymmetric particles, hidden bosons, dark matter candidates, something, anything. But as more collision data arrived, something deeply uncomfortable happened. Nothing appeared. No supersymmetry, no clear new particles, no dramatic deviations, only silence. And that silence began to feel unnatural, because the Higgs discovery had solved the Standard Model's final missing piece, while simultaneously making the entire structure feel suspiciously incomplete. Physics had won, but the victory felt wrong, and as more data poured out of CERN, a disturbing possibility emerged. What if nature was not merely hiding new physics? What if it was hiding it deliberately behind signals so subtle they looked like noise? Soon, CERN's detectors would begin seeing exactly that: tiny deviations, small excesses, anomalies, whispers in the data, and some of those whispers refused to disappear. Success is supposed to bring clarity. In science, a successful prediction is often treated as the closest thing to victory. You build a theory tested against reality, and if nature agrees, confidence grows. But sometimes success becomes unsettling. Sometimes a theory works so well that its perfection begins to feel suspicious. That was the paradox facing particle physics after 2012. The discovery of the Higgs boson should have completed the Standard Model in glorious fashion. Every major particle predicted by the framework had now been observed. Every central mechanism had experimental support. The machine worked, the equations worked. Reality appeared to obey the theory with astonishing precision, and that was exactly the problem, because many physicists had expected the Large Hadron Collider to do more than confirm existing theory. They expected it to expose what came next. The Higgs was supposed to be a doorway, not the destination. Once the door opened, something else should have been waiting on the other side. Instead, there was nothing, at least nothing obvious. To understand why this silence became disturbing, you need to return to the hierarchy problem. On the surface, the Higgs mass seems like just another number in physics, roughly 125 gigaelectron volts. But beneath that number lies one of the most uncomfortable puzzles in modern science. Quantum field theory tells us that empty space is never truly empty. Virtual particles constantly flicker into and out of existence. Even if they exist for unimaginably brief times, they still influence measurable properties of real particles. The Higgs, more than most particles, is especially vulnerable to these quantum corrections. Think of the Higgs field as a calm lake. Now imagine every particle in the universe constantly tossing pebbles into that lake. Ripples spread in every direction. Those ripples alter the energy of the field. In quantum terms, they contribute to the Higgs mass. Here is the disturbing part. Those contributions are enormous, absurdly enormous. If you calculate all known quantum corrections, the Higgs mass should not remain near 125 GeV. It should be driven upward toward incredibly high energy scales, possibly approaching the Planck scale around 1019 GeV. That is not a small mismatch. That is a mismatch of 17 orders of magnitude, a number so large human intuition fails. Imagine expecting a mountain and measuring a grain of sand. That is the scale of the discrepancy. Yet nature somehow cancels these massive contributions with extraordinary precision, leaving behind the small observed Higgs mass. Mathematically, this requires near-perfect balancing between huge, positive, and negative terms. This balancing act became known as fine-tuning, and physicists dislike fine-tuning for good reason. Fine-tuning often signals missing physics. Consider a pencil balanced upright on your fingertip. In principle, such balance is possible. But if you walk into a room and find thousands of pencils perfectly balanced on their tips, you would not assume coincidence. You would suspect a hidden mechanism. Something must be stabilizing them. That was the intuition. The Higgs mass looked unnaturally balanced. There had to be a hidden stabilizer. This belief drove one of the most influential ideas in modern theoretical physics, supersymmetry. Supersymmetry proposed something radical yet elegant. Every known particle would have a heavier partner with different quantum properties. Quarks would have squarks. Electrons would have selectrons. Gluons would have gluinos. Bosons and fermions would gain mirror counterparts. Why did this matter? Because these partner particles could cancel dangerous Higgs corrections naturally. Quantum contributions from ordinary particles would be offset by contributions from supersymmetric partners. The terrifying fine-tuning problem would disappear. The pencil would no longer need miraculous balance. Hidden supports would explain stability. Supersymmetry also offered other benefits. Some supersymmetric particles made excellent dark matter candidates. Certain grand unification models became cleaner under supersymmetry. Even string theory found the symmetry attractive. By the early 2000s, optimism was widespread. Many physicists believed the LHC would discover supersymmetry almost immediately. It made sense. The machine was designed precisely to reach the energy range where these particles might appear. And so, after the Higgs discovery, anticipation shifted. Now, the real discoveries would begin. Run more collisions. Collect more data. Search for excess events. Look for missing energy signatures. Wait for supersymmetric particles to reveal themselves. Months passed. Then years. Nothing. No squarks. No leptons. No gluinos. No clear supersymmetric signatures. The silence became harder to ignore. At first, theorists adjusted parameters. Perhaps partner particles were slightly heavier than expected. Then heavier still. Models evolved. Constraints tightened. Allowed parameter space shrank. Still nothing. This created a strange psychological shift inside physics. Theories once considered natural began feeling increasingly artificial. Each null result forced more tuning, more exceptions, more complexity. Elegant models started accumulating patches, and then a deeper question emerged. What if the assumption itself was wrong? What if nature does not care about naturalness? This question shook the field more than many outsiders realized. Naturalness had guided theoretical physics for decades. It was not a formal law, but it acted like a philosophical compass. Physicists trusted that nature should not require absurd coincidences without deeper explanation. But what if reality simply does? What if some parameters are finely tuned because that is how the universe is? This possibility made many physicists deeply uncomfortable. Because if naturalness fails, one of the most reliable heuristics in theoretical physics may fail with it. And once that happens, prediction becomes much harder. The LHC had not broken the standard model. It had done something more unsettling. It had strengthened it. Every collision confirming standard model predictions narrowed the room for new physics. Every null result increased the tension. The theory's success became oppressive. It was like questioning a suspect whose alibi grows stronger with every new piece of evidence, even while your intuition insists something is wrong. The standard model explained too much, yet not enough. This contradiction became known informally as the nightmare scenario. The nightmare was not that the LHC would fail. The nightmare was that it would succeed perfectly, confirming the standard model while revealing nothing beyond it. No new particles, no clear new forces, no roadmap forward. Just a beautiful but incomplete theory extending farther than expected. For a while that nightmare seemed increasingly real, and then something changed. Tiny irregularities began appearing inside the data, not dramatic discoveries, not headline-worthy particles, something subtler, statistical excesses, unexpected decay ratios, events occurring slightly more often than theory predicted. Most physicists remained cautious. They had seen anomalies before. Particle physics is filled with false alarms. With enough collisions, random fluctuations are inevitable. A few events above expectation mean little on their own, but anomalies have a dangerous habit. They attract attention, especially when they emerge in independent datasets, especially when they hint at energies where new physics might live. At first, these signals were barely whispers, small enough to ignore, easy to dismiss as noise. But whispers become harder to dismiss when multiple people hear them. And around 2015, inside CERN's enormous detectors, a signal emerged that electrified the global physics community almost overnight. 2 photons, an energy near 750 gigaelectron volts, a tiny bump in the data, nothing more. And yet, for a brief, extraordinary moment, physicists around the world believed they might be witnessing the first undeniable crack in the standard model. The whisper had become louder, much louder, and it was about to trigger one of the strangest episodes in modern physics. If you have never worked with scientific data, it is easy to imagine discovery as something dramatic. A clean signal appears. A graph spikes upward. Scientists immediately recognize a breakthrough. Reality is rarely that generous. Most discoveries do not arrive as declarations. They arrive as doubt, a strange point on a graph, a slight deviation, a number that feels wrong. Then a question. Is this real? That question lies at the heart of modern particle physics because CERN does not simply produce discoveries. It produces unimaginable amounts of noise. Every second inside the Large Hadron Collider, hundreds of millions of proton collisions occur. Each collision releases showers of particles rushing outward through detector layers like fragments from microscopic explosions. Most of these events are ordinary, familiar, predictable. They follow well-understood processes described by the standard model. Hidden among them are rare event signals so subtle that finding them can feel like searching for a single unusual raindrop during a hurricane. That is why particle physicists became obsessed with statistics, because intuition fails at these scales. Human pattern recognition is powerful but dangerously flawed. We are evolved to find meaning even where none exists. Faces in clouds, shapes in shadows, patterns in randomness. In high-energy physics, that instinct can be catastrophic. You cannot trust excitement. You cannot trust first impressions. You trust significance. This is where one of the most famous ideas in particle physics enters the story. Sigma? A sigma value measures how likely an observed deviation could arise purely by chance. The larger the sigma, the less likely random fluctuation becomes. A 1 sigma fluctuation happens constantly. 2 sigma is still common. 3 sigma becomes interesting. At roughly 3 sigma, the chance of random occurrence drops to around 0.3%. That sounds compelling. It is not enough. Particle physicists are notoriously cautious because they have been fooled too many times. At CERN and other major experiments, a discovery is not declared until a signal reaches 5 sigma. 5 sigma corresponds to roughly a 1 dash in dash 3.5 dash million chance that the result is random noise. That threshold may seem extreme. It exists for a reason. History. Physics is littered with anomalies that looked revolutionary until they vanished. One of the most famous examples came in 2011. Researchers working with the Opera experiment reported something astonishing. Neutrinos appeared to travel faster than light. If true, the implications were staggering. Faster than light travel would challenge one of the central pillars of modern physics, Einstein's special relativity. News exploded across the world. Headlines hinted at the collapse of established physics. Then came the investigation. The anomaly was not revolutionary physics. It was a loose fiber optic cable. A tiny hardware issue had skewed timing measurements. The universe remained intact. That episode became a cautionary tale. Extraordinary claims demand extraordinary skepticism. And yet, skepticism creates its own tension. Because genuine discoveries often begin as fragile anomalies. The Higgs boson itself did not appear at 5 sigma on day 1. It began as a subtle excess, a small statistical bump gradually strengthened by more data. Every real discovery first looks suspicious. That means physicists live in a strange psychological state. They must remain excited enough to notice something extraordinary, while remaining skeptical enough not to fool themselves. It is a delicate balance, like listening for whispers during a storm. To understand how difficult this is, imagine attending a concert inside a stadium packed with 50,000 people. Everyone is talking. Music blares, noise fills the air. Now imagine someone across the stadium whispers your name. Detecting that whisper is nearly impossible. But if the whisper repeats again and again in a consistent pattern, you begin paying attention. That is how anomalies emerge at CERN, not as obvious discoveries, as recurring whispers. Every collision at the LHC produces enormous datasets. These are reconstructed into measurable quantities: particle energies, momentum, distributions, invariant masses, decay channels, angular patterns missing energy signatures. Physicists compare these observations against theoretical predictions generated by simulations. If reality consistently produces more events than expected in a specific region, that excess becomes interesting. One of the most important tools for this analysis is the invariant mass spectrum. This sounds technical, but the idea is intuitive. Suppose an unknown heavy particle exists. It forms briefly during a collision, then decays into known particles. Even if the original particle disappears instantly, its decay products preserve information about its mass. By measuring those products and reconstructing their combined energy and momentum, physicists can infer the mass of the parent particle. Now imagine plotting millions of such reconstructed events on a graph. Most of the graph forms smooth background distributions. But if a new particle exists, events cluster around a specific mass. That clustering creates a bump, a resonance, a whisper. Particle hunters spend years looking for bumps. Sometimes they find them, and sometimes those bumps trigger madness. By 2015, the Large Hadron Collider had entered a new era. After upgrades, it resumed operation at higher collision energies than before. The increased energy meant something important. If heavier unknown particles existed, the LHC now had better chances of producing them. Expectations surged. This was the moment many theorists had waited for. Supersymmetry might finally appear. Hidden bosons could emerge. Dark matter candidates might reveal themselves through missing energy events. The community watched the first new datasets closely. Then, something unusual happened. Both major detectors, ATLAS collaboration and CMS collaboration, noticed a small excess in events involving 2 photons. 2 photons alone are not unusual. Proton collisions produce photons frequently. But what mattered was the reconstructed invariant mass of those photon pairs. The events clustered near 750 gigaelectron volts. A bump, small, subtle, but real enough to attract attention. The local statistical significance appeared intriguing. Not enough for discovery, not even close, but enough to make physicists lean forward. Why? Because a resonance at 750 GeV had no place in the standard model. Nothing predicted it. Nothing known fit there. If the signal was real, it implied a new particle, not a correction, not a reinterpretation, a genuinely new object in nature. And that possibility changed everything. Within days, excitement spread through the global physics community. Researchers began proposing explanations at astonishing speed. Could it be a heavy Higgs cousin, a graviton from extra dimensions, a supersymmetric state, a portal to dark matter, a sign of composite Higgs physics, a hidden boson from an entirely unknown sector? Theoretical papers exploded. Not dozens, hundreds. Then more than 500. Eventually, nearly 1,000 papers attempted to explain a signal that had not even reached discovery threshold. The field entered a frenzy, and that frenzy revealed something profound. Physics was hungry for cracks in the standard model, hungry for evidence that something deeper existed, hungry enough that even a faint anomaly could ignite worldwide excitement. But hunger is dangerous, because it can distort judgment. And this is what made the next phase so psychologically brutal. More data was coming. Much more. The whisper would either grow louder or disappear into noise. There would be no middle ground. For months, physicists waited. Every conference became charged with anticipation. Every update carried tension. Was the bump growing? Was nature finally revealing something new? Or had the community fallen in love with another illusion? Then the new datasets arrived, and with them came a verdict no one could avoid. The signal at 750 GeV had changed, not strengthened, not sharpened. It was fading. The whisper was disappearing, and soon physicists would face a painful question. Had they just witnessed the future of physics? Or another beautiful statistical mirage? For a few extraordinary months, the future of particle physics seemed to hang on a small bump in a graph. That may sound absurd. Entire scientific revolutions reduced to a tiny statistical excess. But that is often how frontiers work. At the edge of knowledge, dramatic truths rarely announce themselves with thunder. They arrive as slight deviations from expectation. A curve bends where it should remain smooth. A few more events appear than theory allows. A whisper becomes just loud enough to disrupt certainty. The 750 GeV anomaly did exactly that. When researchers inside Atlas Collaboration first examined the diphoton spectrum from the new collision data, the bump was impossible to ignore. It sat near 750 gigaelectron volts, a region where the standard model predicted no new resonance. On its own, one unusual fluctuation might not matter. But then, the second detector CMS collaboration reported hints of a similar excess. That changed the emotional temperature instantly. Independent detectors seeing hints in roughly the same region is exactly the kind of coincidence physicists watch for. Not proof, not even close, but enough to justify intense scrutiny. Suddenly, the possibility of a genuine discovery no longer felt remote. To understand the excitement, imagine two independent weather satellites detecting the early spiral of a storm over the ocean. Neither image proves a hurricane is forming. But if both satellites see rotation in the same region, meteorologists pay attention. They begin asking dangerous questions. Could this become something real? At CERN, the same psychology took hold. Could this bump be the first confirmed sign of physics beyond the standard model? Theoretical physicists moved with astonishing speed. It was as if years of compressed anticipation suddenly found an outlet. Models that had remained dormant were revived. New frameworks emerged overnight. Existing theories were reinterpreted around the anomaly. Seminar rooms filled. Preprint servers surged. The sheer scale of response became almost surreal. In less than a year, hundreds upon hundreds of papers attempted to explain a signal based on incomplete data. Some estimates placed the number near 1,000. Few episodes in modern theoretical physics had triggered such a concentrated intellectual reaction. Why such intensity? Because the anomaly seemed almost too perfect. Its mass scale was intriguing. Heavy enough to suggest genuinely new physics, light enough to remain accessible to the LHC. The decay into two photons implied certain quantum properties. Whatever particle produced the signal could not be arbitrary. It needed very specific characteristics. This constrained speculation, and constraints make anomalies irresistible. One major hypothesis proposed a heavier cousin of the Higgs boson. The standard model contains one Higgs field, but many extended theories predict additional scalar particles. If a second Higgs existed near 750 GeV, the anomaly might fit naturally. Another idea involved supersymmetry. Although standard supersymmetric predictions had failed to materialize, more complex supersymmetric frameworks remained viable. Perhaps the signal reflected one of these hidden sectors. Then came extra dimensions. This possibility captured public imagination because it felt almost science fiction, yet emerged from serious theoretical work. Some models suggest that additional spatial dimensions may exist beyond the three we experience. These dimensions could be compactified, curled so tightly that they escape direct observation. Imagine walking on a tightrope from far away. At great distance, the rope appears one-dimensional. You can move only forward or backward. But an ant standing on the rope experiences another dimension. It can also walk around the circumference. Both perspectives are correct, but scale determines what becomes visible. Extra-dimensional theories propose something similar about reality itself. From human scales, space appears three-dimensional. At microscopic scales, hidden dimensions might emerge. If such dimensions exist, collisions at sufficient energies could briefly excite particles associated with them. Sometimes called Kaluza-Klein modes. A 750 GeV resonance could, in principle, fit such scenarios. Then there were darker possibilities. What if the signal was connected to dark matter? What if the observed photons were only visible remnants of interactions involving an entirely hidden sector of physics? This possibility electrified researchers because it touched one of cosmology's greatest mysteries. Dark matter remains invisible to ordinary light, yet gravitational evidence suggests it dominates galactic mass. For decades, physicists had searched desperately for non-gravitational signatures. A collider-produced mediator particle could become the bridge, a portal between visible matter and hidden matter. The phrase sounded almost poetic, portal, but behind the language was something profound. A new particle could act as a messenger between worlds of physics that had never before communicated. No wonder excitement surged. Yet amid the frenzy, experimental physicists remained cautious. They had lived through anomalies before. They understood something. Theorists often feel, only abstractly, large datasets inevitably produce fluctuations. If you examine enough distributions across enough energy ranges, random bumps will appear somewhere. This statistical trap is known as the look elsewhere effect. It sounds technical, but the logic is simple. Suppose you roll a die 6 times and ask whether 6 consecutive sixes is remarkable. It is. Extremely unlikely. But now imagine millions of people rolling dice continuously worldwide. Somewhere someone will eventually roll 6 sixes. Unlikely events become expected when opportunities multiply. The same principle applies to collider data. CERN does not analyze one graph. It analyzes thousands, across countless energy windows, across numerous decay channels, across different event topologies. If you search enough places, random bumps are inevitable. This means local significance can be misleading. A bump that looks exciting in one narrow region may become much less impressive when accounting for the vast number of places it could have appeared. And this is where the 750 GeV anomaly became psychologically fascinating. Physicists knew the signal might vanish. They understood the statistics, and yet excitement persisted. Why? Because desire influences perception, not through dishonesty, through hope. The field had spent years waiting for something, anything that challenged the standard model. Null results had become exhausting. The Higgs had completed the known picture, but opened no obvious path forward. Theoretical frameworks were increasingly constrained. Many physicists felt trapped between elegant mathematics and stubborn experimental silence. The 750 GeV signal offered escape. It suggested the universe might still surprise us. It suggested the next revolution might already be visible. Then came the waiting. Waiting in science is rarely dramatic from the outside. Inside the field, it can feel unbearable. More collisions were recorded. More events accumulated. More data entered analysis pipelines. Each new batch sharpened reality's answer. If the anomaly reflected a real particle significance, should gradually strengthen. The bump should rise above background with increasing clarity. If it was noise, it would dissolve. There is something brutal about this phase of science. Theory can speculate endlessly. Data eventually decides, and data is indifferent to hope. Conference season arrived. Rumors spread before official presentations. Small hints leaked through conversations, workshops, collaborations. People watched for body language, tone, confidence, hesitation. Then the updated analyses were released. The verdict was devastating. The excess had weakened, not dramatically at first glance, but enough that confidence collapsed. More data did not reinforce the signal. It diluted it. The once promising bump flattened toward background expectation. Statistical significance dropped. The elegant explanations, the portal theories, the extra-dimensional resonances, the hundreds of papers all began evaporating. The signal had not become discovery. It had become noise, just another fluctuation, another whisper swallowed by the storm. For many outsiders, this may sound like failure. Inside physics, the emotional impact ran deeper. The collapse of the 750 GeV anomaly exposed something uncomfortable about the field itself. Not just scientific uncertainty, psychological vulnerability. The community had revealed how desperately it wanted new physics. Hunger had amplified a whisper into near revolution. A fluctuation became a global event. That lesson lingered, because if even experts could become captivated by noise, a dangerous question followed. What if future anomalies were ignored too quickly? What if genuine new physics also began as whispers? The challenge became profound. Avoid false discovery. Avoid false dismissal. Listen carefully. Skepticism protects science, but too much skepticism can blind it. And just as the 750 GeV excitement faded, something stranger began emerging elsewhere. Not a resonance, not a dramatic bump, something subtler. Patterns in particle decay, tiny violations of symmetry, small deviations repeated across independent experiments. Unlike the 750 GeV signal, these anomalies did not disappear quickly. They persisted, quietly, stubbornly. And this time, the whisper was saying something even more unsettling. It was suggesting that one of physics' deepest principles might not be true after all. Physics depends on symmetry more deeply than most people realize. Symmetry in science does not merely mean visual balance or pleasing shapes. It means invariance. A law of nature is symmetric if it remains unchanged under specific transformations. Rotate an experiment. Move it through space. Run it tomorrow instead of today. If the underlying laws remain identical, symmetry holds. These symmetries are not aesthetic luxuries. They are structural pillars. Entire conservation laws emerge from them. Energy conservation, momentum conservation, charge conservation. Remove the right symmetry, and entire pieces of physics collapse. By the early 21st century, One symmetry in particular had become so foundational that few physicists expected it to fail: lepton universality. The name sounds technical, but the principle is simple. Nature should treat the three charged leptons, electrons, muons, and tau particles the same way, apart from differences caused by mass. In other words, if you ignore how heavy they are, the weak force should interact with them identically. The universe should not prefer electrons over muons, or muons over taus. This principle is deeply embedded in the Standard Model. Break it, and something fundamental changes. For decades, experiments supported this symmetry. Again and again, leptons behaved as expected. The Standard Model held. Then, researchers studying rare particle decays began noticing something odd. The anomaly did not appear inside spectacular collisions or exotic resonances. It emerged in decay channels so subtle that even many physicists outside flavor physics initially paid little attention. That changed quickly, because the deviations kept returning. To understand what scientists were measuring, you need to meet a peculiar family of particles called mesons. Mesons are composite particles made of one quark and one antiquark. Most exist only briefly before decaying into lighter particles. Among these B mesons became especially interesting. Why B mesons? Because they contain bottom quarks, heavy particles whose decays are exquisitely sensitive to quantum effects. Rare decay pathways can act like magnifying glasses for hidden physics. Even particles too heavy to be produced directly can subtly influence these decays through quantum loops. Think of it like watching ripples on a pond. You may never see the fish swimming below the surface, but their motion still disturbs the water. In particle physics, rare decays can reveal invisible participants in the quantum background. Experiments such as LHCb collaboration began measuring these decays with increasing precision. Researchers studied how B mesons transformed into lighter particles while producing pairs of leptons. According to the Standard Model, decays producing electron pairs and decays producing muon pairs should occur at predictable relative rates. They did not. Repeatedly, the measured ratios showed fewer muons than expected. Not dramatically fewer, just slightly, but enough to matter. The deviations appeared in observables known as RK and RK asterisk. These quantities compare how often B mesons decay into kaons plus electron pairs versus kaons plus muon pairs. Under lepton universality, these ratios should hover close to 1 after accounting for known corrections. Instead, measurements drifted lower. The deviations were subtle but unsettling. At first, many assumed ordinary explanations would resolve them. Experimental uncertainties, statistical fluctuations, underestimated theoretical errors. Such possibilities are common in precision physics, but then another anomaly appeared, and another. Different observables, different datasets, similar direction. This is what made the situation dangerous. Single anomalies can be dismissed. Correlated anomalies demand attention. By now, a pattern began emerging. Several independent measurements hinted at the same possibility: muons might be behaving differently than electrons in ways the Standard Model could not explain. That implication was explosive, because if leptons are not universal, then some new interaction may be selectively influencing one lepton family more than another. That requires new physics, not optional adjustments. New physics. Physicists immediately began asking, what kind of particle could cause such effects? One candidate gained particular attention: the Z-prime boson. The Standard Model already contains the Z boson, a neutral carrier of the weak force. A heavier cousin, commonly called Z-prime, appears in many beyond Standard Model theories. Such a boson could mediate a previously unknown force that couples differently to muons and electrons. In plain language, this would mean nature contains an additional fundamental interaction beyond the four known forces. That alone would be revolutionary. Another candidate sounded even stranger: leptoquarks. The name reflects their hybrid role. These hypothetical particles can connect quarks and leptons directly in ways impossible under ordinary standard model interactions. If leptoquarks exist, they could alter rare meson decays naturally. This idea fascinated theorists because it hinted at something deeper. Maybe quarks and leptons are not truly separate categories. Maybe they are related through hidden symmetries yet to be discovered. The implications expanded rapidly. If flavor anomalies were real, they might represent the first experimental cracks in one of particle physics' deepest assumptions. But there was a problem. The evidence remained frustratingly incomplete. Statistical significance hovered in the intriguing but not definitive regime. Not weak enough to ignore. Not strong enough to declare discovery. The anomalies lived in scientific limbo. This limbo produced intense debate. Some physicists became increasingly convinced that flavor physics was pointing toward new, fundamental interactions. Others urged caution, emphasizing the difficulty of precision calculations involving hadronic effects. Quantum chromodynamics. The theory describing strong interactions is notoriously difficult in certain regimes. Small theoretical uncertainties can mimic anomalies. Both sides had valid arguments, and this is what made the story so compelling. No one could dismiss the data outright. No one could claim victory either. The field entered a state of suspended tension. Then something remarkable happened. The anomalies stopped feeling isolated, because another completely different experiment using entirely different methods, involving an entirely different observable, began reporting deviations that pointed in a disturbingly similar direction. And at the center of this new anomaly stood one particle. A particle so ordinary it passes through your body constantly. A particle many people have never even heard of. The muon. At first glance, the muon seems unremarkable. It behaves almost exactly like an electron, except heavier, about 200 times heavier. It carries the same electric charge. It participates in the same electromagnetic interactions. Yet, that extra mass makes it extraordinarily sensitive to hidden quantum effects. Why? Because heavier particles interact more strongly with certain quantum corrections. If unknown particles exist in the vacuum, muons feel their influence more strongly than electrons. That makes muons perfect probes for new physics. And when scientists measured one specific property of the muon with extreme precision, the result sent a shock through the field. The measurement disagreed with theoretical expectation, not by much, but enough. Enough to become one of the most persistent anomalies in modern physics. Enough to raise a disturbing possibility. What if empty space itself was hiding unseen particles? What if the vacuum around you was not merely active, but populated by physics we still do not understand? The whispers from CERN were no longer confined to collider events. Now they pointed towards something even stranger, the quantum vacuum itself. And the muon was about to reveal why empty space may be one of the most misleading phrases in science. If you could shrink yourself down into the quantum world and watch particles moving through space, the muon might not be the first thing to catch your attention. It does not glow. It does not live long. It is unstable, decaying in just 2.2 microseconds into lighter particles. In cosmic terms, that lifetime is almost nothing. Blink and it is gone. And yet, this fleeting particle has become one of the most powerful tools for probing hidden reality. The muon was discovered in 1936 by Carl D. Anderson while studying cosmic rays. Its discovery confused physicists so deeply that one famous reaction became legendary. When told of the particle, Isidore Isaac Rabi reportedly asked who ordered that the question captured the absurdity of the moment. The muon seemed unnecessary. It behaved almost exactly like an electron, except far heavier and unstable. It appeared to add complexity without explanation. Decades later, that unnecessary particle would become a possible messenger of new physics. The key lies in one subtle property: spin. In classical intuition, spin sounds like literal rotation, as if particles are tiny spinning spheres. That image is misleading. Quantum spin is intrinsic angular momentum, a built-in property of particles more fundamental than ordinary rotation. Still, the spinning analogy remains useful because charged spinning objects behave like tiny magnets. That means muons act like microscopic compass needles. Place them in a magnetic field and they wobble. Physicists call this wobble precession. You have seen an everyday version of this if you have watched a spinning top begin to tilt and circle as it slows. Instead of falling directly, it precesses around an axis. A muon in a magnetic field does something mathematically similar. Now comes the important part. The rate of that wobble can be predicted with extraordinary precision. Why? Because every interaction affecting the muon contributes slightly to its magnetic behavior. Electromagnetism contributes. Weak interactions contribute. Strong interactions contribute indirectly through quantum loops. Even virtual particles flickering into existence inside the vacuum alter the wobble by tiny amounts. This makes the muon a quantum detector, not because it records collisions like CERN's giant instruments, because its motion encodes the influence of everything interacting with it, even particles too heavy or too rare to observe directly. Imagine floating in a perfectly calm lake on a small boat. You cannot see beneath the surface, but if unseen fish move below, subtle ripples disturb your boat. By carefully measuring those ripples, you infer hidden activity underwater. That is the muon. Its wobble becomes a readout of invisible quantum disturbances. Physicists describe this behavior using a quantity called the magnetic moment. In simple terms, it measures how strongly the muon responds to magnetic fields. Quantum theory predicts a value extremely close to 2, but not exactly 2. Tiny corrections from vacuum fluctuations shift the value slightly. This deviation is called the anomalous magnetic moment, commonly written as G2. That tiny anomaly became one of the most important numbers in modern physics. Because if the measured value differs from theoretical prediction, something is missing from the theory. Something in the vacuum is influencing the muon that physicists failed to account for. This possibility drove one of the most precise experiments ever attempted. The first major hints emerged at Brookhaven National Laboratory in the early 2000s. There, physicists accelerated muons into a giant magnetic storage ring and measured how their spins precessed while circulating at high speed. The results were astonishing. The measured wobble differed from standard model predictions, not dramatically, but consistently. The discrepancy sat at a level large enough to trigger serious interest. At first, caution dominated. Precision physics is merciless. Tiny systematic errors can produce misleading results. Theoretical calculations involving hadronic contributions remained difficult. Experimental uncertainties had to be scrutinized relentlessly. No one wanted another false alarm, so the scientific community waited for better measurements. That led to one of the most ambitious precision experiments in recent memory, the muon G2 experiment at Fermilab. Even transporting the apparatus became legendary. The massive superconducting magnetic ring, 14 meters in diameter, could not simply be rebuilt easily. It was moved intact from New York to Illinois in a carefully orchestrated journey involving barge transport roads and extraordinary engineering. The move became symbolic. Physics was literally carrying one of its biggest questions across the country. At Fermilab, the experiment resumed with improved instrumentation and higher precision. Muons were injected into the magnetic ring and circulated thousands of times. As they decayed, detectors captured the timing and energy of emitted particles, allowing researchers to reconstruct spin precession with exquisite accuracy. Years of data collection followed. Then came April 2021. The world watched. Physicists gathered for the announcement. Excitement was palpable because everyone understood the stakes. If Fermilab confirmed Brookhaven's discrepancy, the anomaly would become far harder to dismiss. The results were revealed. The discrepancy remained, and the combined significance approached 4.2 sigma, not discovery threshold, but deeply compelling. The standard model prediction and experimental measurement no longer aligned comfortably. Something was off, something subtle but persistent. The muon was wobbling too much. That sentence sounds harmless. It is not, because extra wobble means extra influence. Extra influence implies missing contributions. Missing contributions imply missing physics, and suddenly the question became unavoidable. What was interacting with the muon? Theoretical possibilities exploded. Supersymmetric particles returned to discussion. Hidden photons, dark sector bosons, leptoquarks, new scalar fields, unknown force carriers. Even extremely weakly interacting particles could alter the muon's magnetic moment through quantum loops. The anomaly became a battlefield of competing explanations. But then an important complication emerged. Theory itself became contested. The experimental measurement was not the only challenge. The standard model prediction depends on complex calculations, especially contributions from strong interaction effects involving quarks and gluons. These hadronic contributions are notoriously difficult to compute. Different methods produced slightly different results. Some lattice quantum chromodynamics calculations suggested the discrepancy might shrink. That changed the conversation. Was the anomaly experimental evidence of new physics, or evidence that theoretical calculations were incomplete? This distinction mattered enormously, because if theory shifts enough, the anomaly weakens. And yet, even with theoretical uncertainty, one fact remained deeply intriguing. The muon anomaly was not isolated anymore. Remember the flavor anomalies from rare B meson decays? They also involved muons. This coincidence became difficult to ignore. Two independent lines of evidence, different experiments, different observables, same particle. The muon kept appearing at the center of unexplained deviations. That pattern unsettled physicists, because patterns matter. When independent anomalies point toward the same sector, attention sharpens. The whispers begin harmonizing, and that raised a more radical possibility. What if the muon was not special by accident? What if muons are especially sensitive because hidden physics couples preferentially to them? That would explain both classes of anomalies. A new force interacting strongly with muons could distort rare decays and alter magnetic precession simultaneously. Such a force would represent something extraordinary, a fifth fundamental force. Not gravity, not electromagnetism, not strong nuclear, not weak nuclear. Something new, entirely new. The implications stretched far beyond particle physics. Because if new particles are influencing muons through vacuum fluctuations, then the vacuum around you is even stranger than quantum mechanics already suggests. This brings us to the most unsettling realization of all. The vacuum is not empty, not remotely. The space between atoms, planets, stars, and galaxies may look like nothing. But quantum physics says that nothing is violently active. Particles flicker into existence and vanish. Energy fluctuates. Fields never truly rest. And if hidden particles exist, they may already be present there, invisible, undetected, constantly shaping reality. The muon may be sensing them. Which raises a disturbing question. If empty space is full of invisible activity, what exactly is emptiness? And what else might be hiding inside the vacuum itself? When you think of empty space, your mind probably imagines silence. No matter, no motion, no structure, just nothing. It feels intuitive. Between stars lies darkness. Between atoms lies emptiness. Between galaxies stretches vast cosmic void. For centuries, emptiness was treated as the absence of everything. Even in classical physics, vacuum was often described as a stage and empty background upon which matter and energy performed. Quantum physics destroyed that idea completely. In the quantum universe, emptiness does not exist in the way human intuition expects. What you call empty space is not an inactive void. It is a restless medium filled with invisible fields, fluctuating energy, and ceaseless microscopic activity. The vacuum is not silent, it hums, and that hum may be one of the reasons anomalies at CERN refuse to fully disappear. To understand why you need to let go of one deeply rooted assumption that particles are the fundamental fabric of reality. Modern quantum field theory tells a stranger story. Fields come first, particles come second. This reversal is profound. Earlier in our journey, you encountered the idea that every fundamental particle corresponds to a quantum field extending throughout all space. The electron field exists everywhere. The quark fields exist everywhere. The photon field fills the cosmos. Even if a region contains no detectable particles, the fields themselves remain present. That means empty space is never truly empty. It is filled with fields even when no particles are observed, and fields possess a peculiar property. They cannot remain perfectly still. At first, this seems counterintuitive. Why should a field in vacuum fluctuate at all? Why would nothing vibrate? The answer comes from one of the strangest principles in physics, the uncertainty principle. Most people associate Werner Heisenberg with uncertainty in position and momentum. But uncertainty runs deeper. Quantum systems cannot simultaneously possess perfectly precise values for certain pairs of physical quantities. One consequence is startling. Even the lowest energy vacuum state cannot have exactly zero energy. Perfect stillness is forbidden. There must always be residual fluctuation. Think of a guitar string. In classical physics, a string can lie completely motionless. In quantum physics, even the lowest energy state retains tiny, unavoidable vibrations. It never becomes perfectly still. Now, replace the guitar string with every quantum field in existence. Suddenly, the vacuum becomes active. Constantly, everywhere. These fluctuations create what physicists call zero-point energy. And once zero-point energy exists, something even stranger becomes possible: virtual particles. The phrase is widely used, but often misunderstood. Virtual particles are not ordinary particles popping into reality like miniature fireworks. They are mathematical expressions describing temporary quantum disturbances inside interactions. Still, the imagery remains useful because these disturbances behave as if particles briefly appear and disappear. Pairs of particles and antiparticles flicker into existence, then vanish, again and again, everywhere. Imagine the vacuum as the surface of boiling water. At first glance, the surface may appear calm, but look closely, and bubbles constantly form, rise, and collapse. The quantum vacuum behaves similarly, except the bubbling occurs on incomprehensibly tiny scales. This activity is not philosophical speculation. It produces measurable consequences. One famous example is the Casimir effect. Place two uncharged metal plates extremely close together inside a vacuum. Quantum fluctuations between the plates become restricted compared with fluctuations outside. This imbalance creates a measurable force pushing the plates together. Nothing touches them. No conventional force pulls them. Yet they move, because the vacuum itself exerts pressure. That result changed how physicists think about emptiness. Vacuum behaves like a physical medium, not passive emptiness, active structure. And this brings us back to the muon. Why does vacuum activity matter for particle physics? Because particles moving through space constantly interact with vacuum fluctuations. As a muon travels, it is not moving through nothing. It is moving through a storm of quantum activity. Virtual photons appear. Virtual quark pairs fluctuate. Weak bosons contribute tiny corrections. Every interaction slightly alters measurable properties. This is why the muon's magnetic moment becomes so powerful. It acts like a sensor for vacuum structure. If known quantum fluctuations cannot fully explain its wobble, one possibility becomes irresistible. Unknown fluctuations may exist. Unknown particles may be bubbling through the vacuum. Particles we have never directly observed. This idea transforms how you think about discovery. You may imagine new particles as rare objects waiting to be created inside giant colliders. But what if some new particles already permeate space around you, invisible, silent, undetected only because they interact too weakly with ordinary matter? CERN's collisions might not be creating something entirely new. They might be briefly illuminating something already present. That possibility opens the door to one of the most compelling ideas in modern physics' hidden sectors. The Standard Model describes known particles and forces with incredible success. But nothing guarantees it describes all quantum fields in existence. There may be additional sectors containing particles that rarely interact with visible matter. These sectors could coexist with our familiar universe, almost like overlapping realities, not alternate universes in a science fiction sense, overlapping quantum structures. Imagine two radio stations broadcasting through the same room. Both signals coexist in the same physical space, yet your radio only receives the frequency it is tuned to. Hidden sector physics works similarly. New particles may exist around us constantly, but our matter may barely couple to them. Unless high-energy collisions briefly tune into their frequency, that is one reason CERN matters so much. It allows physicists to disturb the vacuum violently enough that hidden interactions might leave fingerprints. Missing energy events, unusual decays, excess particle production, subtle anomalies, whispers, and hidden sectors connect naturally to an even bigger mystery: dark matter. Astronomers have spent decades accumulating evidence that most matter in the universe is invisible. Galaxies rotate too quickly. Galaxy clusters bend light more strongly than visible mass allows. Cosmic structure formation requires additional gravitational influence. Something unseen dominates cosmic mass. Something real, but invisible. The Standard Model offers no confirmed explanation. This makes the vacuum even more mysterious. Because if dark matter particles exist, where are they? One unsettling answer is simple: everywhere. You are moving through dark matter right now. Earth is moving through it. The solar system is moving through a halo of it. Galaxies are embedded in vast dark matter structures. Yet ordinary matter barely notices. This realization changes scale. The anomalies at CERN may not merely concern missing particles in equations. They may be indirect glimpses of the invisible majority of the universe. That thought is almost difficult to absorb. Everything humans have ever seen. Every planet. Star nebula. Black hole. Galaxy atom. Body civilization accounts for only a small fraction of cosmic matter energy. We are the visible minority, and that means the deepest question becomes unavoidable. What exactly is the dark universe made of? If the vacuum hides unseen particles, if muons feel their influence, if CERN's anomalies are real, then perhaps the whispers are pointing towards something vast, not just a new particle, not just a new force, a hidden cosmic architecture, an unseen universe woven through our own. And if that is true, the next question becomes extraordinary. Can CERN do more than detect the dark universe? Could it actually create pieces of it? Look around you. Everything you can see, your hands, the screen in front of you, the air, buildings, oceans, planets, stars, even the blazing heart of the Milky Way feels substantial. It feels complete. Human intuition quietly assumes visible matter is the universe. After all, sight dominates perception. We trust what we can observe, but modern cosmology delivers a deeply unsettling correction. Almost everything you can see is not the universe. It is the exception. By current measurements, ordinary matter, the atoms composing everything familiar, accounts for only about 5% of the total cosmic energy budget. 5%. That means roughly 95% of the universe consists of something we do not directly understand. About 27% appears to be dark matter, an invisible form of matter detected only through gravity. Roughly 68% appears to be dark energy, an even more mysterious component driving the accelerated expansion of the universe. pause on that. The physics governing nearly all cosmic content remains incomplete. That alone explains why anomalies at CERN matter so much. The standard model may describe visible matter beautifully, but visible matter is only a tiny fraction of reality. A theory explaining 5% of the universe cannot be the final story. The question is no longer whether physics is incomplete. It is how incomplete. The evidence for dark matter did not arrive all at once. It emerged slowly through a century of astronomical discomfort. Early hints appeared in the 1930s when Fritz Zwicky studied the Coma cluster of galaxies. He noticed something strange. The galaxies were moving far too quickly to remain gravitationally bound if only visible matter existed. By Newtonian expectations, the cluster should fly apart. It did not. Zwicky proposed that unseen mass must be holding it together. He called it Dunkelmaterie, dark matter. At the time, few appreciated how profound this idea was. Decades later, stronger evidence emerged, this time from galactic rotation. If you study stars orbiting within a galaxy, classical physics gives a clear expectation. Stars near the center should orbit faster because more mass lies inside their orbit. Stars farther outward should slow down much like planets in the solar system. Neptune moves more slowly around the Sun than Mercury because gravitational influence weakens with distance. Galaxies refuse to obey. When astronomer Vera Rubin measured rotation curves of spiral galaxies, she found something astonishing. Outer stars were not slowing as expected. They were moving almost as fast as inner stars. This should not happen unless the visible galaxy sat inside a much larger invisible halo of mass. Imagine spinning a glowing merry-go-round at night. You only see the lights attached to the visible structure. But the rotation tells you there must be a massive hidden framework extending far beyond the lights. That hidden framework is the dark matter halo. The conclusion became increasingly unavoidable. Galaxies are embedded inside invisible matter. Then came gravitational lensing. Einstein's general relativity predicts that mass bends space-time and light follows that curvature. Massive objects therefore distort background light like cosmic lenses. By measuring how galaxies and clusters bend light, astronomers can map total mass, even invisible mass. Again, visible matter was not enough. Again, something unseen dominated. And then came one of the most dramatic pieces of evidence, the bullet cluster. Two galaxy clusters had collided. Ordinary matter, especially hot gas, interacted strongly and slowed during the collision. But gravitational lensing revealed that most mass passed through with minimal interaction, remaining offset from the visible gas. This observation mattered enormously, because it suggested dark matter is not merely modified gravity or mathematical illusion. It behaves like real matter, invisible matter, matter that gravitates but barely interacts with light. By now, dark matter had become one of modern science's most compelling mysteries. But what is it? This question is where cosmology meets particle physics. The standard model contains neutrinos, which are nearly invisible and weakly interacting. Could neutrinos explain dark matter? Not sufficiently. They are too light and too fast-moving to explain observed large-scale structure. Something else is needed. That realization triggered decades of theoretical speculation. Among the most famous candidates are WIMP's weakly interacting massive particles. The idea is elegant. Dark matter could consist of heavy particles interacting through forces similar in strength to the weak nuclear force, but otherwise remaining invisible to electromagnetic detection. This possibility became especially attractive because of a remarkable coincidence called the WIMP miracle. Calculations showed that particles with masses around the electroweak scale and weak force interaction strengths naturally produce relic abundances close to observed dark matter density, and that energy scale overlaps with the energies probed by the Large Hadron Collider. This changed everything, because suddenly CERN was not merely a machine for testing abstract theories. It became a dark matter factory candidate. In principle, If dark matter particles can be produced in high-energy collisions, the LHC might create them directly. But a problem immediately appears. Dark matter, by definition, barely interacts with detectors. If produced, such particles would simply escape, invisible, untouched. How do you detect something that leaves no trace? You look for absence. This sounds paradoxical, but absence can be measurable. At CERN, collisions obey conservation laws. Energy and momentum must balance. Physicists carefully reconstruct every visible particle emerging from a collision. If something invisible carries energy away, the visible products no longer balance as expected. The missing quantity becomes evidence. This observable is called missing transverse momentum, often shortened to missing energy. Imagine playing billiards on a frictionless table. You strike one ball into a cluster. After the collision, all visible balls scatter. If momentum appears unbalanced, if one direction carries unexplained motion, you infer an unseen ball must have participated. Collider physicists do something similar. They hunt invisible particles by measuring imbalance. And this is where dark matter searches at CERN become both thrilling and frustrating. The LHC has recorded many events involving missing energy signatures. Most are perfectly explained by known particles, such as neutrinos, which also escape detection. The challenge lies in distinguishing ordinary invisible particles from extraordinary ones. That requires subtle pattern analysis. Event topology, associated jets, photon signatures, lepton production, rare decay pathways, tiny statistical excesses. Again, discovery does not arrive dramatically. It whispers. Over the years, numerous searches for dark matter signatures at CERN have constrained models, ruled out parameter spaces, and sharpened theoretical understanding. Yet no definitive collider-produced dark matter particle has been confirmed. No breakthrough, no smoking gun, only narrowing possibilities. But something important has changed. Physicists no longer assume dark matter must be a single simple particle. Theoretical frameworks have evolved dramatically. Hidden sectors, dark photons, axion-like particles, strongly interacting dark sectors. Freeze-in scenarios, possibilities now span vast landscapes. Some models suggest dark matter may exist within entire hidden ecosystems containing multiple particles and forces invisible to us. Not just one missing particle, an unseen particle civilization. That idea may sound fantastical, but modern theory increasingly entertains such complexity. And if dark sectors exist, CERN might not detect dark matter directly. It might detect messenger particles, bridges, portals connecting visible and hidden sectors. This possibility brings us back to anomalies, because not every strange event at CERN looks like missing energy. Some look stranger. Energy balances correctly. Known particles appear. Yet the event topology feels wrong. Tracks begin where no particle should emerge. Decays happen too late. Particles seem to live too long. Signals refuse clean explanation. These rare events have created some of the most puzzling questions in collider physics. They hint at something even more unsettling than dark matter. Because if certain anomalies are real, they may suggest not merely invisible particles, but new dimensions of reality itself. And that possibility forces us to confront one of the boldest ideas in theoretical physics. What if our universe contains more dimensions than the ones you experience every day? At CERN, some of the most important discoveries begin with something that isn't there. That sounds impossible at first. Science, after all, is built on observation. You detect particles, measure energies, reconstruct trajectories, and compare results with theory. Discovery seems tied to presence. Something appears in the detector. Something leaves a measurable trace. But in high-energy physics, absence can be just as revealing as presence. Sometimes what matters most is not what you see. It is what should have been there, but wasn't. This idea lies at the heart of missing energy events, one of the most powerful and mysterious tools in modern collider physics. These events do not announce themselves through spectacular explosions or obvious new particles. They announce themselves through imbalance, through accounting errors in nature's ledger. And nature is not supposed to make accounting errors. Every proton collision inside the Large Hadron Collider obeys conservation laws with ruthless consistency. Energy and momentum cannot simply vanish. They can change form. They can spread across many particles, but the total balance must remain intact. That means if visible particles emerging from a collision do not account for the expected energy flow, something unseen must have carried the missing portion away. Something invisible, something the detector did not register. To understand why this matters, imagine standing in the center of a frozen lake at night while friends throw glowing balls outward in every direction. If you carefully measure the motion of every visible ball, the total momentum should balance. But suppose the glowing balls suddenly recoil strongly toward one side, even though no visible object traveled in the opposite direction. Something must have pushed them. Even if you cannot see it, an invisible object must have carried momentum away. That is the logic of missing energy. At CERN, physicists reconstruct collision debris with extraordinary precision using massive detectors such as ATLAS collaboration and CMS collaboration. These detectors act like layered digital eyes. Inner tracking systems record charged particle paths. Calorimeters measure deposited energy. Muon chambers detect deeply penetrating particles. Magnetic fields bend trajectories, revealing momentum and charge. By combining all this information, scientists rebuild each collision event like forensic investigators reconstructing an explosion. Most events balance beautifully, but not all. Some events show significant missing transverse momentum. The word transverse matters here. Inside the collider, proton beams travel in opposite directions along the beam pipe. The exact longitudinal energy of individual colliding quarks and gluons is uncertain because protons are composite objects. But perpendicular to the beam direction, total momentum should begin near zero. That makes transverse imbalance especially revealing. If large transverse momentum appears missing, something escaped. Often, the explanation is completely ordinary. Neutrinos. Neutrinos are infamous for their near invisibility. They carry no electric charge and interact only through the weak force and gravity. Billions pass through your body every second without consequence. At CERN, neutrinos frequently escape detectors producing missing energy signatures. This is expected. It is not mysterious. The real challenge lies in distinguishing ordinary missing energy from extraordinary missing energy. Because dark matter candidates would behave similarly. They would escape. They would carry momentum away. They would leave no direct signal. That means dark matter and neutrinos can produce superficially similar detector signatures. This creates one of collider physics' most difficult problems. How do you separate known invisible particles from unknown invisible particles? The answer lies in patterns. Physicists do not analyze missing energy alone. They analyze the entire event topology surrounding it. Associated jets, photon emissions, muons, electron pairs, angular distributions, correlations, rare decay chains. Imagine hearing footsteps in a house at night. Footsteps alone tell little. But the pattern matters. Slow pacing suggests one story. Running suggests another. Irregular movement suggests something stranger. Context transforms interpretation. The same is true at CERN. Missing energy becomes meaningful only through surrounding evidence. This has led to several major search strategies. One of the most famous is the monojet search. In these events, collisions produce one extremely energetic jet, a spray of particles from a quark or gluon recoiling against large missing energy. The visible jet acts like a tracer. If an invisible particle pair is produced, the jet may be the only visible sign. Picture firing a cannon in darkness. You never see the cannonball, but you feel the cannon recoil violently backward. That recoil proves something massive moved forward. Monojet events work similarly. The visible jet recoils against something unseen. This makes them prime dark matter candidates. Over years of data collection, thousands of such events have been studied. Most align with standard model expectations involving neutrinos. But each search narrows the range of viable dark matter models. Still, missing energy events have produced something even more intriguing than dark matter searches. Anomalous topologies, rare events where the problem is not just missing energy, but event structure itself. Some collisions produce tracks that appear to start in empty space. This should not happen. Ordinarily, charged particles emerge from the collision point near the beam interaction region. Their tracks radiate outward predictably. But in certain rare cases, reconstructed tracks seem displaced. They begin centimeters away, sometimes farther. That implies something extraordinary. A particle may have been produced at the collision point, but traveled invisibly for a short distance before decaying into visible particles later. Physicists call these displaced vertices. They are among the most exciting signatures in collider physics. Why? Because long-lived particles are difficult to produce within the standard model at detectable scales. Significant displaced decays often hint at exotic possibilities. Hidden sectors, heavy neutral leptons, dark bosons, supersymmetric states, or portal particles connecting visible and invisible matter. Imagine lightning striking a field, but instead of thunder occurring immediately, the thunder happens seconds later from an empty patch of sky some distance away. That delay would feel impossible. Displaced vertices create a similar feeling inside detectors. The event sequence feels wrong. Nature appears to hesitate. These signatures fascinate physicists because they may reveal entirely new sectors of reality with weak couplings to ordinary matter. A hidden particle might live long enough to travel measurable distances before decaying back into visible particles. In effect, the particle briefly disappears from our detectable universe, then returns. This idea sounds almost surreal, yet it emerges naturally in serious theoretical models. And this is where CERN's anomalies become more unsettling, because some of the strangest events cannot be explained cleanly by simple dark matter models or standard model backgrounds. They remain rare, often statistically weak, never strong enough for discovery, yet stubborn enough to sustain interest. And the deeper physicists looked, the more one possibility refused to disappear. What if the missing energy is not merely due to invisible particles escaping into ordinary space? What if energy is leaking somewhere else? Not elsewhere geographically, elsewhere dimensionally. This sounds like science fiction until you realize modern theoretical physics has spent decades entertaining exactly such possibilities. Extraspatial dimensions, hidden geometric directions beyond human perception. And if such dimensions exist, collisions at sufficiently high energies might do something extraordinary. They might briefly open access to them. Particles could carry energy into dimensions our detectors cannot directly observe. From our perspective, that energy would simply vanish, not destroyed, not lost, transferred beyond our accessible slice of reality. This possibility remains speculative, but it touches one of the boldest ideas ever proposed in physics. Because if extra dimensions are real, the universe may be far larger and far stranger than three-dimensional intuition allows. The missing energy events at CERN may not just hint at hidden particles, they may hint at hidden geometry. And that possibility leads directly to one of the most radical questions in modern science. How many dimensions does reality actually have? You experience the universe in 3 dimensions, forward and backward, left and right, up and down. Add time, and you have the 4-dimensional spacetime described by Albert Einstein. This framework has explained gravity, black holes, cosmic expansion, and the motion of galaxies with extraordinary success. It feels complete because human experience is built inside it. But what if completeness is an illusion? What if the universe contains more dimensions than your senses can perceive? This idea sounds like pure fantasy until you realize it emerged not from science fiction, but from mathematics, specifically from repeated attempts to unify the deepest laws of physics. The first serious step came more than a century ago. In the 1920s, Physicists Theodore Kaluza and Oscar Klein proposed something audacious. Einstein's equations beautifully described gravity in four-dimensional spacetime. But what if you added one extra spatial dimension? Surprisingly, the mathematics produced something extraordinary. Gravity remained, but another familiar force appeared naturally inside the equations: electromagnetism. This was astonishing. By adding a fifth dimension, two seemingly separate forces could emerge from one geometric framework. It hinted at a profound possibility. Perhaps forces are not separate fundamental entities at all. Perhaps they are manifestations of geometry in higher dimensional space. This idea was revolutionary, but it raised an obvious question. If extra dimensions exist, why don't we see them? Klein offered an elegant answer. Perhaps the extra dimension is compactified, curled up, tiny beyond imagination. To visualize this, imagine a garden hose lying across a field. From far away, the hose appears one-dimensional. You see only length. A distant observer might conclude movement is possible only forward or backward. But an ant walking on the hose experiences another dimension. It can also move around the circumference. The extra dimension was always there. It was hidden by scale. This analogy became foundational in higher dimensional physics. Reality may contain additional directions too small for everyday perception. For decades, this idea remained mathematically interesting, but experimentally inaccessible. Then, modern theoretical physics pushed it much further. String theory changed the scale of ambition. Unlike conventional particle physics, which treats particles as point-like objects, string theory proposes that fundamental particles are tiny vibrating strings. Different vibration modes produce different particles. Electrons correspond to one vibrational pattern. Quarks correspond to another. Force carriers correspond to others. At first glance, this sounds abstract, but the deeper consequence mattered more. The mathematics refused to work in only four dimensions. Consistent string theory required extra dimensions, not one. Many, depending on the formulation, 10 or even 11 total dimensions emerged naturally. This was no arbitrary choice. Without extra dimensions, the equations broke. That forced physicists into an extraordinary possibility. The universe may fundamentally contain far more dimensions than human perception reveals. Some dimensions could be compactified at microscopic scales. Others might be larger, yet hidden through geometric constraints. This radically changed how physicists imagined reality. Three-dimensional space might be only a visible slice of something much larger. Imagine living on a sheet of paper. Creatures confined to that sheet experience only length and width. They cannot perceive height directly. A three-dimensional object passing through their world would appear bizarre. First a point, then a growing circle, then a shrinking circle, then nothing. They would observe strange manifestations without perceiving the full object. That analogy became powerful. What if humans are similarly confined? What if our universe is effectively a lower dimensional slice embedded in higher dimensional space? This brings us to one of the boldest frameworks in modern theoretical physics, brain-world models. In these models, ordinary matter and familiar forces may be confined to a three-dimensional membrane called a brain embedded in higher dimensional space. Electromagnetism remains trapped. Strong interactions remain trapped. Weak interactions remain trapped. But gravity may not. Gravity could leak into extra dimensions. This idea became especially attractive because it offered a possible explanation for one of physics' biggest puzzles: why gravity is so weak compared to other forces. Consider a simple comparison. A small refrigerator magnet can lift a paperclip against the gravitational pull of the entire Earth. That should feel absurd. The Earth contains nearly 6 sextillion kilograms of mass. Yet a tiny magnet overcomes its pull effortlessly. This reveals something profound. Gravity is extraordinarily weak compared to electromagnetism. Why? One possibility is startling. Gravity may only appear weak because much of its influence spreads into extra dimensions. Imagine shouting inside a narrow hallway. Your voice remains concentrated and loud. Now, imagine shouting in an enormous open valley. The sound spreads in all directions and weakens rapidly. If gravity spreads into hidden dimensions while other forces remain confined, its apparent weakness becomes understandable. And this is where CERN enters the story again. Because if extra dimensions exist, sufficiently energetic collisions might reveal them, not by showing dimensions directly, by exposing their consequences. There are several ways this could happen. One possibility involves Kaluza-Klein excitations, heavier versions of known particles arising from momentum in extra dimensions. These would appear as new resonances in collider data. Another possibility involves gravitons. In quantum gravity theories, gravitons are hypothetical particles carrying gravitational interaction. If gravity accesses extra dimensions, gravitons produced at CERN might escape into higher dimensional space. From our detectors, that would look familiar. Missing energy. Energy appears to vanish, not destroyed. Escaped. This possibility made missing energy searches especially important. Some anomalous events became interesting not just as dark matter candidates, but as possible evidence of extra-dimensional leakage. Then came an even more provocative idea: microscopic black holes. Few ideas captured public imagination more dramatically. When the LHC first began operating, headlines exploded with fear. Could proton collisions create black holes that consume Earth? The answer from physicists was clear: no. Even if microscopic black holes could form, they would evaporate almost instantly through Hawking radiation. They would pose no threat. Still, the fact that serious physics allowed discussion of collider-created black holes was astonishing. Why was this even possible? Because in some extra-dimensional models, the true energy scale, where gravity becomes strong, could be much lower than traditionally expected. Instead of requiring unreachable Planck-scale energies, microscopic black holes might form at TV scales accessible to colliders. If such black holes formed, they would decay explosively into many particles. CERN has searched extensively for such signatures. No confirmed evidence has emerged. But the search itself reveals how radical modern physics has become. We are no longer merely searching for new particles. We are testing the geometry of reality itself. And yet, the strangest possibility is still ahead. Because extra dimensions, hidden sectors, dark matter, and long-lived particles all point toward a deeper question. What if the anomalies are not random at all? What if some collision events genuinely reflect phenomena that current physics cannot classify? Over the years, a handful of rare collision signatures have done exactly that. Not enough for discovery. Too strange for comfort. Events with patterns that resist clean explanation. Signals that do not fit expectations. Events experimental physicists return to repeatedly because something about them feels wrong. And these are the moments that unsettle science most. Not clear discoveries, not clear errors, ambiguity. Because ambiguity forces a terrifying possibility. What if the data is already trying to tell us something, and we still do not understand the language? Most particle collisions at CERN are boring. That may sound strange, given the extraordinary energies involved, but boring in physics does not mean unimportant. It means predictable. Billions upon billions of collisions occur exactly as theory expects. Quarks scatter, gluons fragment, jets form, bosons decay. Detectors record familiar patterns. The standard model once again proves frighteningly accurate. And that is precisely why rare anomalies matter so much. When an event appears that resists immediate explanation, physicists pay attention not because they assume new physics, but because unexplained events occupy a dangerous zone between discovery and error. Most eventually become understood. Detector noise, calibration drift, reconstruction artifacts, statistical coincidence. Yet a tiny fraction linger. Those lingering events create unease, because they raise a deeply uncomfortable question. What if reality has already shown us something extraordinary and we failed to recognize it? To understand why this possibility is taken seriously, you need to appreciate how collider experiments interpret events. Detectors do not produce photographs of microscopic collisions. They produce raw electronic signals, voltages, timing pulses, energy deposits. These signals are converted through complex reconstruction algorithms into tracks, vertices, particle identities, and event topologies. In other words, every collision passes through layers of interpretation. This matters enormously, because seeing a particle at CERN is never as simple as observing an object directly. It is more like reconstructing a crime scene from footprints, fingerprints, broken glass, and witness testimony. The reconstruction can be incredibly accurate, but only if your models are correct. What happens if the event does not resemble anything your models expect? That is where impossible events begin. Imagine a language translation system, trained on every known language, suddenly receiving a message in an unfamiliar script. The system may misclassify symbols, force patterns into familiar categories, or fail entirely. In collider physics, something similar can happen when genuinely unusual events occur. Reconstruction pipelines are optimized around known physics. Truly novel phenomena may not fit cleanly. This creates a paradox. New physics may be hardest to recognize, precisely because it does not resemble old physics. One class of unsettling signatures involves long-lived particles, which we touched on earlier. These hypothetical particles can travel measurable distances before decaying, producing displaced vertices far from the collision point. Such events already feel strange, because nature appears to delay part of the collision outcome. But some signatures become stranger still. Tracks that abruptly disappear. Charged particles entering detector layers and then vanishing. No expected decay chain. No conventional explanation. These are called disappearing tracks. Under standard model expectations, charged particles should leave continuous detectable paths until they decay or lose energy. But certain beyond standard model scenarios, especially compressed supersymmetric models, predict charged particles that transform into nearly invisible neutral particles after traveling short distances. The visible track simply ends. No explosion, no obvious decay products, just disappearance. This is deeply unsettling from a detector perspective. Imagine watching airplane radar and seeing a plane traveling normally before its signal abruptly stops mid-flight with no crash signature. Even if technical explanations exist, your attention sharpens instantly. CERN has recorded events resembling such signatures, though none with sufficient significance to establish discovery. Most are ultimately explainable through detector inefficiencies or background processes. Yet the search remains active because disappearing tracks could reveal hidden sectors or exotic particle transitions. Then there are delayed signals. These events challenge intuition in a different way. Most collision products reach detector components within predictable time windows. But some rare signals arrive late. Slightly delayed energy deposits, unexpected timing offsets, decay products appearing later than standard event reconstruction expects. Again, most delayed events have mundane explanations. Instrumentation affects cosmic rays, background contamination. But some theoretical models predict exactly such delays from heavy, long-lived particles moving slower than ordinary relativistic particles. In these scenarios, timing itself becomes evidence, not energy, not mass, time. And then there are events so rare and structurally odd that they gain near mythical status among physicists. Unusual multilepton events, exotic jet structures, unexpected combinations of missing energy and displaced signatures. Events where several individually plausible anomalies combine into something psychologically difficult to dismiss. These cases rarely become public headlines because scientists understand how misleading anecdotal events can be. one weird event proves almost nothing statistically. But among experimental collaborations, such events often become subjects of intense internal discussion. The reason is subtle but important. Not every discovery begins statistically. Sometimes the first clue is conceptual discomfort. An event feels wrong before it becomes significant. It violates intuition developed from years of pattern recognition. Physicists rarely say this publicly because science demands formal evidence, not gut feeling. Yet experienced analysts develop something akin to detector intuition. They know what ordinary data feels like, and sometimes something feels off. This human element matters more than outsiders realize. We often imagine science as purely algorithmic, but discovery frequently begins when trained intuition notices an inconsistency that formal models have not yet captured. Algorithms process data at enormous scale. Humans notice weirdness. This brings us to one of the strangest possibilities in collider physics. What if some anomalous events are not merely signs of new particles, but signs that our theoretical categories themselves are incomplete? This possibility becomes increasingly relevant as searches broaden beyond conventional frameworks. For decades, collider searches often targeted specific theories, supersymmetry, extra dimensions, heavy bosons. But repeated null results changed strategy. Physicists began asking a harder question. What if new physics does not resemble our favorite theories at all? This question triggered the rise of model-independent searches. Instead of testing one theory at a time, researchers now increasingly scan for deviations from expected event distributions without committing to specific models. Machine learning systems help identify anomalous patterns in enormous datasets. Algorithms search for outliers events unlike anything predicted by standard model simulations. This approach is powerful. It is also unsettling because it admits something profound. Physics may not know what it is looking for. That statement would have sounded shocking decades ago. Today, it feels increasingly honest. We know the standard model is incomplete. We know dark matter exists. We know gravity resists unification. We know cosmology demands new understanding, but the shape of what comes next remains deeply uncertain. That uncertainty transforms anomalies. A strange event is no longer judged solely against known alternative theories. It may represent something we have not imagined, and this is why the impossible events at CERN matter even when none qualifies as discovery. They remind physicists of an uncomfortable truth. Absence of confirmed discovery is not evidence of complete understanding. Reality may already be producing signatures of new physics that hide inside ambiguity detector limitations or theoretical blind spots. The anomalies may not be too small. They may be too unfamiliar. This realization changes how the future must be approached. Because if current machines cannot clearly resolve these whispers, physics faces an unavoidable conclusion. We need more power, more precision, more collisions, more sensitivity, a larger machine, a deeper probe into reality. And that ambition has already taken shape. Scientists are now designing what may become the most powerful scientific instrument ever built, a machine capable of reaching energies far beyond the Large Hadron Collider, a machine that could either silence the whispers forever or amplify them into undeniable truth. The next chapter of particle physics may not begin with a new theory. It may begin with a new collider. There comes a point in every scientific era when progress collides with limits. Not limits of imagination, not limits of curiosity, limits of tools. You can only observe so much with a telescope of a certain size. You can only sequence so much biology with a given resolution. And in particle physics, you can only probe so deeply into reality with a machine of finite energy. That is where modern physics stands today. The Large Hadron Collider has transformed our understanding of matter. It delivered the Higgs boson. It tested the standard model at unprecedented precision. It ruled out vast regions of theoretical parameter space. It sharpened our understanding of what nature is not. But that final phrase matters. What nature is not. the LHC has been extraordinarily powerful at exclusion. And exclusions are valuable. They prune bad theories. They force clearer thinking. They narrow possibilities. Yet, exclusion alone does not produce the next paradigm. At some point, physics needs direct discovery, something undeniable, something new. That need has sparked one of the most ambitious engineering proposals in scientific history, a machine beyond the LHC, a collider so vast that even the current 27-kilometer ring begins to look modest. This proposal is known as the Future Circular Collider, often shortened to FCCC, and an initiative centered around CERN. Its scale is difficult to absorb. The proposed tunnel would stretch roughly 90 to 100 kilometers around the Geneva Basin, nearly 4 times the circumference of the Large Hadron Collider. If built, it would become one of the largest scientific structures humanity has ever created. Why so large? Because energy is expensive, not financially though. That matters too. Physically, charged particles moving in circular paths lose energy through radiation, especially lighter particles such as electrons. Reaching dramatically higher collision energies requires stronger magnetic fields, larger radii, or both. Bigger rings allow particles to accelerate to higher energies before bending losses become prohibitive. In simple terms, if the LHC is a Formula One track designed for extreme speed, the Future Circular Collider is an intercontinental highway built for velocities approaching the practical limits of accelerator technology. And the energies under discussion are staggering. The proton-proton phase of the FCC could potentially reach collision energies around 100 teraelectron volts. Compare that with the LHC's design energy of 14 TeV. This is not a modest upgrade. It is a leap large enough to change what is experimentally accessible. Why does that matter? Because many candidate theories predicting new physics may live just beyond the LHC's reach. A hidden particle too heavy for today's collider might become routine at 100 TeV. Entire sectors of theory currently inaccessible could suddenly become testable. Imagine standing at the shoreline of a vast ocean during fog. The LHC allowed us to see far enough to confirm nearby islands and map familiar waters. But if the fog hides distant continents just beyond the horizon, a more powerful machine may finally reveal them. That is the promise. And perhaps the necessity. The scientific goals of a next-generation collider are breathtaking in scope. First, precision Higgs physics. The Higgs boson may already be discovered, but its deeper properties remain only partially measured. Does it interact exactly as the standard model predicts? Does it self-interact in expected ways? Are there subtle deviations revealing hidden sectors? These questions matter because the Higgs may be more than just another particle. It may be a portal. A precision Higgs factory could expose tiny discrepancies invisible to current experiments. Second, dark matter. A higher energy collider expands the mass range of producible dark matter candidates and mediator particles. Hidden sectors inaccessible today could become detectable tomorrow. Third, new force carriers, Z-prime bosons, dark photons, heavy scalars, leptoquarks, composite resonances. Many hypothetical particles become far easier to detect at higher energies. Fourth, long-lived exotic states. Improved detectors and dedicated experiments could dramatically improve sensitivity to displaced vertices and hidden sector signatures. And then there is the deepest goal of all. New principles. This may be the most exciting possibility because history teaches something remarkable when humanity opens a dramatically new observational window. Discovery often arrives from the unexpected. Galileo Galilei did not know he would see the moons of Jupiter when he improved telescopes. Edwin Hubble did not expect to reveal cosmic expansion simply by looking deeper into the sky. Even the discovery of cosmic microwave background radiation emerged from engineers trying to remove annoying noise from an antenna. Sometimes the greatest discoveries are the ones no proposal predicted. This argument has become central to collider advocacy. We should not build larger machines only to test existing theories. We build them because nature still surprises us, because reality still hides things we do not yet know how to ask, yet not everyone agrees. The future of collider physics has become increasingly controversial. The cost of the FCC could reach tens of billions of dollars. Construction would take decades. Political commitment across nations would be essential. Critics argue such resources might yield greater scientific return if distributed across smaller experiments, astrophysical observatories, quantum sensing, or dark matter detection programs. This debate is not trivial. It reflects a deeper tension in modern science. Should progress come from larger centralized machines, or from diversified experimental strategies? Many physicists argue the answer is both, because no single approach can solve every mystery. Dark matter may reveal itself through underground detectors. Quantum gravity may emerge through cosmology. Hidden sectors may surface through tabletop precision experiments. Gravitational wave astronomy may uncover entirely new physics. And yet, collider physics retains a unique power: control. At CERN, physicists do not merely observe nature. They engineer conditions. They recreate energies from the infant universe. They trigger processes on demand. That control makes colliders uniquely powerful tools for causal discovery. This matters because the unanswered questions remain profound. What stabilizes the Higgs mass? Why does matter dominate antimatter? What is dark matter? Why is gravity so weak? Are there hidden dimensions? Are there new forces? The LHC has sharpened these questions, but has not resolved them. That leaves physics in a strange position. We understand more than any civilization before us, and yet the deepest mysteries remain intact, perhaps even more mysterious than before, because every answer has exposed larger unknowns, and that leads to the most unsettling possibility of all. What if the anomalies at CERN are not isolated curiosities? What if they are fragments of a coherent, deeper reality just beyond current resolution? Imagine looking at a blurred image. Individual pixels seem random, noise, artifacts. But increase resolution slightly, and scattered pixels suddenly form structure. A face, a pattern, a message. That may be where physics stands now. The whispers remain below certainty, but perhaps not below truth. And if that is true, then the final question is unavoidable. What happens if the whispers are real? What happens if nature is trying to tell us something profound, and we are finally close enough to hear it clearly? For centuries, science has moved forward through a simple but powerful assumption. The universe is understandable, not easy to understand, not quick to understand, but understandable. That belief carried humanity from stone tools to spacecraft, from firelight to quantum mechanics, from myths about the heavens to measurements of black holes. Every generation inherited mysteries that seemed permanent only to watch some of them dissolve under observation mathematics and experiment. And yet, every major breakthrough has delivered the same paradox. The more we learn, the stranger reality becomes. That is the story of CERN. On paper, the mission sounds straightforward. Accelerate particles, smash them together, study the debris, infer deeper structure. But what began as a machine for finding particles has become something much larger. CERN is no longer merely a laboratory for particle collisions. It is a laboratory for epistemology, a machine that tests not just matter, but the limits of human understanding. And that is why the anomalies matter so deeply. Taken individually, most anomalies remain inconclusive. The 750 GeV diphoton excess faded into statistical history. Flavor anomalies have fluctuated as new datasets arrived. Muon measurements remain provocative, but entangled with theoretical uncertainty. Missing energy events continue to constrain possibilities without revealing a smoking gun. Long-lived particle signatures remain tantalizing, but unconfirmed. None of these anomalies alone overturns physics. That is important to state clearly. There has been no confirmed discovery of physics beyond the standard model at CERN. No proven fifth force. No confirmed supersymmetric particle. no verified extra dimension, no confirmed dark matter production. Science demands honesty, and honesty requires resisting dramatic conclusions unsupported by evidence. But honesty also requires something else: recognizing unresolved tension. Because while no single anomaly has crossed discovery threshold, the deeper discomfort has never disappeared. The standard model remains astonishingly successful. Too successful, some physicists would say. It predicts enormous ranges of phenomena with breathtaking precision. It explains the behavior of quarks, leptons, bosons, and interactions across scales tested in laboratories worldwide. It survives challenge after challenge, and still it cannot be final. That statement is not philosophical, it is unavoidable. The standard model does not explain dark matter. It does not explain dark energy. It does not unify gravity with quantum mechanics. It does not explain the baryon asymmetry that allowed matter to dominate antimatter. It does not explain neutrino masses naturally. It does not resolve the hierarchy problem cleanly. A theory that fails to explain most cosmic mass energy cannot be complete, so we live with a contradiction. Our best theory is extraordinarily right and fundamentally incomplete. That contradiction may define the present era of physics more than any anomaly. We stand in a strange historical position, similar perhaps to late 19th century physics. At that time, many believed the major laws of nature had been discovered. Newtonian mechanics explained motion. Maxwell unified electricity and magnetism. Classical thermodynamics described heat and energy. Only a few anomalies remained: black body radiation, the photoelectric effect, Mercury's orbit, small problems, minor cracks. Then those cracks shattered classical physics. Quantum mechanics emerged. Relativity rewrote space and time. Reality transformed. History offers a warning. Paradigm shifts rarely announce themselves as revolutions. They begin as discomfort, small inconsistencies, persistent anomalies, whispers. That historical analogy is why CERN's unresolved signals remain psychologically powerful even without confirmed discovery. Not because every anomaly predicts revolution. Most will vanish. Some already have. But because scientific revolutions often begin exactly this way, with data that does not quite fit, with equations that feel too delicate, with theories that work too well while leaving too much unexplained. The most unsettling possibility is not that CERN has found something dramatic and hidden it. It is subtler, more profound. What if nature is already revealing new physics, but in forms we are not yet equipped to recognize? This possibility deserves serious reflection. Human cognition evolved to interpret macroscopic environments, predators, landscapes, weather movement. We did not evolve to intuit quantum fields, curved space-time, or hidden dimensions. Mathematics extends our perception, but even mathematics depends on conceptual frameworks shaped by human minds. What if those frameworks themselves impose limits? What if some future discovery requires conceptual tools we have not yet invented? This thought humbles science without diminishing it. Because science has never been about certainty, science is a method for navigating uncertainty, a disciplined way of listening. And listening may be the most important metaphor here. Throughout this journey, anomalies have been described as whispers. That metaphor matters. Whispers are easy to mishear. Background noise can imitate them. Desire can fabricate them. Fear can distort them. Hearing a whisper requires patience, silence, careful repetition, and sometimes entirely new instruments. That may be the true meaning of CERN's unresolved mysteries. Not that physics has failed, not that the standard model is collapsing tomorrow, but that reality remains richer than our current descriptions. There is still structure hidden below resolution, still signal below certainty, still meaning below noise. Perhaps the next collider will reveal it. Perhaps precision cosmology will. Perhaps quantum sensing experiments. Perhaps gravitational wave observatories. Perhaps something no one has yet imagined. History suggests one thing with confidence. Nature always has another layer. Every time humanity believed it had reached bedrock, deeper structure appeared. Atoms gave way to nuclei. Nuclei gave way to quarks. Space gave way to spacetime. Vacuum gave way to quantum fields. Certainty gave way to deeper mystery. And perhaps that is the deepest lesson CERN offers. The goal of science is not to eliminate mystery, it is to refine it. Primitive mysteries become better mysteries. Questions sharpen. Ignorance becomes structured. And structured ignorance is powerful because it tells us where to look next. Deep beneath the Earth, protons still race through superconducting tunnels at velocities approaching light. They collide, they explode into showers of particles. Detectors record impossible torrents of information. Algorithms search. Physicists argue. The machine listens. And somewhere inside those collisions may already exist the first clear fingerprints of the next revolution. Perhaps hidden in rare decays. Perhaps buried in statistical noise. Perhaps waiting for more data. Perhaps waiting for a better question. That may be the most profound realization of all. Discovery is not always about finding answers. Sometimes it is about learning how to ask the right question. So, after everything we have seen after the Higgs, the anomalies, the muon mystery, the dark universe, the hidden dimensions, the impossible events, one truth remains. CERN has not failed to explain reality. It has revealed how much reality still refuses to explain itself. And that leaves us with a final question. If the universe still hides deeper layers beneath everything we know, what else right now is real, but still invisible to us?